This differential equation, the field of partial differential equations, has a long history in mathematics. And once Black and Scholes developed their partial differential equation, they could draw on this vast literature of mathematics and solving partial differential equations, and were able to solve this partial differential equation using some of the same tools that are common in the field of partial differential equations. And it turns out that the call-price formula, this price formula we've seen before, is in fact a solution of that differential equation. It solves that differential equation, and it has the correct boundary value, namely at time capital T, the value of that price function. This is C of ST. This price function satisfies that partial differential equation, and also at when little t is equal to capital T, it has the exercise value of a call. It's exactly the same story for a put. The Black-Scholes price for a put option also satisfies this differential equation, but of course it has a different boundary value. Consequently, it's a different price. There are other securities that you can readily check satisfy this differential equation. Admittedly, taking the derivatives of the call and put price functions are a little bit more challenging to verify that they satisfy the equation. But certainly, these three price functions are not terribly challenging to differentiate, and you should check that they all satisfy. One, for example, is a risk-free zero. Might be remarkable to you that a risk-free zero satisfies this differential equation, and it's a zero that has a terminal value of V of capital T when at time capital T. And you can think of this as a derivative on S that pays V of T no matter what the price of S is. So you could argue that it's a fairly elementary derivative security based on S, and it's a security that no matter what the price of S is, it pays the constant value V of T. So that's a derivative security, however trivial, and therefore it must satisfy the differential equation. A prepaid forward, this is F0TP of S. A prepaid forward contract on S is a security we can buy today. It has a price at every point in time. Again, we can verify that this has satisfies the differential equation, and what's its terminal value? S of capital T. It's a derivative security that satisfies the differential equation and has a terminal value at time capital T equal to the stock price at time capital T. A forward contract on S with a fixed strike. We have a forward contract that we've negotiated, and it has a forward price of K. K's fixed. This is a security that we can buy and sell today, has value positive or negative depending on the value of K and the other parameters. This is a security on S. It indeed is a derivative security based on S. It therefore must satisfy this differential equation. And we can see that when time little t equals capital T, at expiry, it's equal to the profit on a forward contract, namely S of capital T minus K, which is exactly what we think of as the terminal value of a forward contract with fixed K. Now, perhaps surprisingly, there are some contracts that you might think should satisfy the differential equation that don't. The most elementary example of one that doesn't is S. The stock price itself will only satisfy the differential equation if it's a stock with no dividends. Because remember, if we have a stock price that reflects dividends, S is the price of a share. And consequently, when we implement if we put S into this differential equation, we don't get 0, we get minus delta S. And the reason is that this differential equation ignores what happens to the dividends that are paid on the share. And so what the differential equation is telling you is that if you account for the dividends that the stock pays, then indeed the stock will satisfy the differential equation. Without the dividends, the value of those derivatives comes out to be minus delta S. And if you add back the delta S return over an infinitesimal period coming from dividends, you get back to 0. So if delta is 0, the stock itself satisfies the differential equation. If the delta is not 0, it does not, and that the differential equation will come up short. It'll be equal to minus delta S, and you'll need to add back dividends to get back to 0. And this is logical because the Black-Scholes differential equation only reflects the capital gain or loss, not the total return. Another security that you might intuitively think is a forward contract, the forward price on S. It's easy to think that the forward price on S should satisfy the differential equation, but remember, a forward price, this is F0t on S, is not a value of a contract today. This is simply a price that you and I would agree to today that will change hands at time t in return for S, one share of stock. So it is not the price of a derivative security today. The prepaid forward is the price of a security today, and we saw that the prepaid forward indeed satisfies this differential equation. But the forward price itself does not satisfy this differential equation. If you substitute the forward price in, you get a minus RV. Now, what sense does that make? Well, first of all, you could say, well, the forward price isn't really a price today of anything. It's a future price. The reason the Black-Scholes provides you with a minus RV is that the forward price will grow at rate R. We know that the forward price of a security will grow at the risk-free rate as you move through time. And what we see is that when we substitute in the Black-Scholes equation, this is like the stock with dividends, it's telling you that you're going to come up short, and in order to get a total return of 0, you have to add back in the appreciation of the forward price. Other securities that satisfy the Black-Scholes equation are securities that we're going to see in Chapter 22, so-called asset or nothing, cash or nothing options, gap options. We already saw those in an earlier chapter. All of these examples satisfy the Black-Scholes equation, as well as the boundary condition which defines the exercise values.